Imagine stepping into a machine, twisting a dial, and emerging decades in the past, or jumping ahead to meet your future descendants. It's the stuff of science fiction. Yet beneath the cinematic drama lies real physics asking whether time travel might ever be more than a daydream. First, let's talk about moving forward in time, because that part is not only possible but happening around us right now. In Einstein's special relativity, time isn't a universal constant ticking at the same rate for everyone. Instead, it slows down for anything moving close to the speed of light. If you could board a spaceship and accelerate to 99.9% of light speed, then come home after what felt like a few weeks, you might find that years have passed on Earth. This time dilation isn't theory alone. Particle accelerators routinely confirm that unstable particles live longer at high speeds, and precise atomic clocks on fast jets show minuscule but measurable lags. Even without sci-fi rockets, GPS satellites must correct for both their speed and the weaker gravity they experience in orbit, or they drift into error in minutes. Gravity offers another route to the future. In general relativity, massive bodies curve spacetime, and clocks deeper in a gravity well tick more slowly. A clock on Mount Everest runs slightly faster than one at sea level. Again, the effect is tiny, microseconds over a lifetime, but it proves that simply changing elevation is a form of time travel into the future. But what about traveling to the past? Here things get thorny. General relativity's equations admit solutions called closed time-like curves, paths through spacetime that loop back on themselves. The most famous examples are traversable wormholes, hypothetical tunnels connecting distant points in space and time. If you could hold open a wormhole mouth with exotic matter with negative energy density, and move that mouth at relativistic speeds, or near a black hole's gravity, its clock would desynchronize from the other mouth. Enter the slow mouth and exit the fast one to emerge in its past. It sounds like a cheat code for history, but the hurdles are immense. Exotic matter may not exist in quantities sufficient to stabilize a macroscopic wormhole, and tidal forces near the throat would likely spaghettify any traveler. Worse yet, wormholes bring paradoxes. The notorious grandfather paradox, where you travel back and prevent your own birth, seems to break logic. One proposed resolution invokes quantum mechanics and the many worlds interpretation. Any action you take in the past creates a new branch of reality, so you never actually change your original timeline. Your past self lives on in another universe where you never arrived. It's a tidy fix for paradoxes, yet it multiplies realities and remains untestable. Other exotic proposals, cosmic strings, rotating black holes, and Tipler cylinders, infinitely long spinning matter, also hint at closed loops in time. Cosmic strings are theoretical defects in spacetime left over from the universe's birth, capable of warping spacetime enough to create time loops if arranged just right. Tipler cylinders would require an infinitely long, rapidly spinning cylinder, clearly an idealization. In every case, physics papers show that the energy, scale, or ideal conditions needed are far beyond practical reach, if they're even allowed by the deeper laws of quantum gravity. Speaking of quantum, it further muddles the picture. On the tiniest scales, 10 to the negative 35th meters and 10 to the negative 43rd seconds, spacetime may froth into a quantum foam of fleeting wormholes and fluctuations. Some argue that in this realm, exotic time loops could wink in and out of existence. Yet harnessing such phenomena for macroscopic time travel remains pure speculation. Attempts to use quantum tunneling or entanglement for backward causation haven't yielded a way to send usable information to the past. They reveal the strangeness of quantum measurement rather than a workable time machine. Amid all this, Stephen Hawking suggested a chronology protection conjecture, an elegant phrase asserting that the laws of physics prevent macroscopic time machines from forming. He argued that quantum effects near a would-be time loop would blow it up before it stabilized, preserving causality and preventing history-scrambling adventures. Meanwhile, the best-tested physics tells us that forward time travel is not only real but everyday. Our fastest jets, our orbiting satellites, and even our own high-speed particles experience it. Flying around the world at near light speed, if we could, would age you less than your friends on Earth. Climb a mountain and you'll tick just a tiny bit faster than someone at sea level. These are small effects now, but they remind us that time is flexible, not fixed. Culture's fascination with time machines, H.G. Wells's Traveler, Doc Brown's DeLorean, the Doctor's TARDIS, springs from deep human desires to undo mistakes, to relive happier moments, or to glimpse an unknown future. Fiction bypasses energy, requirements, and exotic physics, leaning on paradoxes for drama. Real science, by contrast, demands rigor, negative energy that obeys all laws, stability under quantum fluctuations, and a mechanism to enter and exit safely. In laboratories and observatories, physicists continue probing relativity to new precision. Atomic clocks in Germany and the US have measured gravitational time dilation over a change in height of mere centimeters. Particle physicists track unstable particles for evidence of exotic behaviors. At the same time, theoreticians wrestle with string theory, loop quantum gravity, and the holographic principle, searching for a consistent quantum theory of space-time, one that might illuminate whether time loops or backward travel are fundamentally forbidden or just fantastically difficult. So where does that leave us, dear traveler? For now, hopping backward in time remains in the realm of careful thought experiments and imaginative fiction. But speeding ahead, well, every astronaut exemplifies that leap. And someday, as we push spacecraft ever faster and venture deeper into gravity wells, the future travel side of time travel could become more than scientifically real. It could become an everyday reality, if only by nanoseconds. Until then, when you see a movie hero rewriting the past, remember the real-world constraints, the need for negative energy, the fearsome tidal forces of wormholes, the paradoxes lurking in closed loops, and the potential quantum firewalls that might keep chronology intact. Real-time travel to the past may be blocked by the verdict of physics, but the journey forward into the future is a daily adventure. Every tick of your clock carries you forward, faster or slower, shaped by your speed and gravity. And perhaps that's the greatest marvel. We ride through time every moment, our personal time machines powered by physics itself. So cherish each second, each nanosecond of dilation, because even without a fancy flux capacitor, we're all travelers in time, bound for tomorrow, one heartbeat at a time.